In this chapter section, we will discuss spontaneous redox reactions and the device that based on the spontaneous redox reaction, which is called galvanic cell or voltaic cell. The detail of this chapter can be found on the OER textbook, chapter 18.2. In this video, we will take a look at different reaction between metals and different solution. We are going to write the balanced chemical equation and observe what is happening when you react different metal to different solution, and we will also predict spontaneity of the process as well. Let's take a look at example A. Example A, we are going to react magnesium metal in the copper 2 sulfate solution. So I'm going to go ahead start with writing the chemical equation here. Magnesium metal, the physical state of magnesium would be in solid. Okay, and it react with copper 2 sulfate. Copper 2 refer to the charge of 2 plus on the copper, and sulfate is SO4 2 minus. Therefore, to write the correct chemical formula, you will need 1-to-1 ratio between copper and sulfate. So it's going to be just CuSO4 in this case. And it says solution, so we are going to use the AQ to represent that. Okay, and this reaction, when it happen, is going to displace the metal that you have, which is magnesium, is going to displace the copper ions. Therefore, in this case, the product would be magnesium sulfate, and you are going to end up with the copper metal. So this is an example of redox reaction because magnesium 0 oxidation number become magnesium 2 plus, right? Magnesium sulfate. And copper is going from copper 2 plus to copper 0, which is the solid. So therefore, this is an example of a redox reaction. And picture on your right is the picture of the copper sulfate solution that have blue color. And this is the magnesium strip. So this is the initial state where you have magnesium that is about to react with copper sulfate. Okay, so we are going to observe whether this reaction will occur or not. If this reaction occur, you will start to observe that the magnesium will start to disappear, and you are going to start to see the formation of copper. And also because copper sulfate is blue, right? So this copper sulfate solution here is blue, and magnesium sulfate solution is colorless. Okay, so this is colorless. Therefore, if this reaction happen, you are going to see the change going from blue, which is the identity of copper sulfate solution, to no color at all, or colorless solution that is belong to magnesium sulfate. So let's take a look at the reaction what happen after we react magnesium with copper. When you dip magnesium strip into copper sulfate, you will see that the reaction happening, right? Because there is a formation of the copper solid on the bottom of the test tube, and also you will see that the color of the blue solution become like more fading color, right? So it's eventually, if you leave this long enough, this solution will become colorless. So the observation here is that you will see that the color of copper sulfate change from blue to less blue, and also you see the formation of copper solid is being formed. And because when you add the magnesium strip into copper sulfate, you will see the reaction happen right away, and it doesn't need any ongoing outside intervention. Therefore, this process would consider to be a spontaneous process in the forward direction, because when you react these two together, eventually it spontaneously react to form magnesium sulfate, which is colorless, and copper solid that you observe here. Therefore, spontaneity would be spontaneous in the forward direction. Next, we will take a look at the reaction between copper, solid copper metal, and the zinc sulfate. We are going to react copper, or we are going to dip copper strip into zinc sulfate solution, and we will make an observation what happened. Okay, and also eventually we will predict the spontaneity of this process. So first, let's take a look at the balanced chemical equation of this first. So I'm going to do the same thing. We have copper solid that react with zinc sulfate, and when it's undergo chemical reaction, the copper will displace the zinc. Therefore, in this case, it's going to become copper sulfate and zinc metal. Okay, if this reaction happen, you are going to end up seeing the formation of solid zinc, okay, on the bottom of beaker. And also we just see earlier that the copper sulfate solution, from what we see on the previous step, it has a color of blue. Therefore, you are going to see the formation of the blue color of the solution as well if this reaction is actually spontaneous. And you probably already see that the color of zinc sulfate is colorless, right? There is no color, right? So as you absorb here, there is no color, it's colorless. Therefore, if this reaction happen, if copper actually react with zinc sulfate, it's going to go from colorless solution into blue solution, and you are also going to observe zinc sulfate to form as well. So let's take a look at what happened. When you dip copper strip into zinc sulfate solution and you wait, still nothing happened. There is no formation of zinc in the beaker and the color of the solution doesn't change at all. And therefore, in this case, this redox reaction that we see here is not going to happen. Okay, so because there is no reaction, so I'm going to write X over the arrow. It just tells you that the reaction doesn't proceed forward, which means that it will not form copper sulfate or zinc. Therefore, in this case, we can write a observation that nothing happened, right? So that would be our observation. Therefore, the conclusion for the spontaneity for this process would be it is non-spontaneous in the forward direction because the reaction doesn't proceed at all. So it's non-spontaneous in the forward direction. And because it's non-spontaneous in the forward direction, it's also implied that the reverse direction is spontaneous, which means that it's most likely to just stay as the reactant. It doesn't want to go forward toward product. However, if you start with these two products as reactant, it is actually going to react and then proceed to the reverse direction. Next, let's take a look at the reaction between zinc metal and copper sulfate. Okay, so in this case, we are going to write a balanced chemical equation, which is solid zinc strip react with copper sulfate aqueous, and it's going to undergo displacement, which means it's going to become, this reaction is a redox reaction because zinc 0 would become zinc sulfate 2 plus, right? And then copper 2 plus will become copper solid, okay? So again, if this reaction happen, what you are going to observe is that you are going to observe the color of copper sulfate, which is blue, okay? So exactly what you see here, right? That's the color of copper sulfate. That's the zinc strip. And it's going to become zinc sulfate, which is colorless. And you can see from the previous example, right? Like the zinc sulfate is colorless. There is no color here, right? So therefore, what you are going to observe is if this reaction is happen, it's going to changing from the blue color to colorless, or from like a darker blue to a lighter blue. But if you wait long enough, you are going to observe the colorless solution, which is the identity of the zinc sulfate. And you're also going to observe copper that deposit into the beaker as well. Okay, so now let's take a look at observation here. And here, once you dip zinc strip into copper sulfate, you will see that the zinc strip change color into a copper color, and you see that the color of the solution become lighter blue, right? So therefore, in this case, we see that the blue color of copper sulfate is become lighter blue because they are forming more of the zinc sulfate. And if you wait long enough, this color will become colorless. And you also see the formation of copper that deposit on the zinc strip as well. So the observation of this would be solution change color from blue to lighter blue, or eventually would be colorless, and copper is formed on the zinc strip. Therefore, this redox reaction is considered to be spontaneous redox reaction in the forward direction, because when these two react, it's going to proceed forward toward the product to form more of the product. Okay, so it would be spontaneous in the forward direction. It's also implied that because this reaction is spontaneous in the forward direction, therefore if you have the reverse direction, which means that when you have copper and zinc sulfate going to the reverse direction, it would be non-spontaneous in the reverse direction, which makes sense because if you compare the example B and C, the difference between these two is that you are swapping between the reactant and product, right? So from copper plus zinc sulfate, this is reactant now, and it doesn't happen because non-spontaneous in the forward. But in example C, the zinc sulfate and copper now become product. Therefore, in this case, it's not going to be spontaneous in the reverse direction because the reverse direction is non-spontaneous. We already confirmed that as part B. Right, so similar to what we talked about in part PB earlier as well, if you have these two starting, it's going to be spontaneous in the reverse direction because it's non-spontaneous in the forward direction. So it's described the same thing. Okay, so it's just swapping between the reactant and the products, so that way you can confirm, right? If the forward is non-spontaneous, then the reverse would be spontaneous. Vice versa, if the forward reaction is spontaneous, then the reverse direction would be non-spontaneous. We already confirmed that. Next, we are going to look at the device that based on the redox reaction, except this device, the physical state between the reactant are prevented, which means that the two reactants will not in direct contact with each other, but the transfer of electron would take place indirectly through an external circuit. And this type of device is called electrochemical cells. There are two types of electrochemical cells. One is galvanic cell or voltaic cell, and another is called electrolysis cell. The difference between these two is that the first one, which is the galvanic cell or voltaic cell, is based off spontaneous reaction, and the electrolysis is based off non-spontaneous redox reaction. First, we will put our focus on the galvanic cell or voltaic cell that based on the spontaneous redox reaction. I'm going to use the reaction between silver ions and copper as an example of galvanic cell. As you see, silver ions, silver plus, it doesn't come with any negative charge. So this would be an example of net ionic equation, which means you already eliminate the spectator ions. Therefore, this solution right here, it would come from, for example, silver nitrate or silver acetate that are soluble. So that's why you don't see any solid form in there, right? So these would be the soluble silver ions, right, that come from there. And these silver ions would react with the copper, right? So this is the copper wired. So in this case, again, of those negative anions are not going to participate in the reaction. Therefore, it doesn't appear in the net ionic equation. So what happened in this case is that the copper is going to be the one that gives off its electron to silver. So in this case, copper would then become copper 2 plus. Okay. And the reason why I know it's copper 2 plus because as you see at the end, the color that is formed, right, is blue color, and that is the identity of the copper 2 plus. You see this before in copper sulfate. And as you see, the copper sulfate, the copper ion in copper sulfate is copper 2 plus that gives the blue color. And the other species that it would form would be silver, solid silver. Okay, so pretty much as you see here, because silver ion solution has no color, then it will become color of blue because that's the identity of the copper 2 plus. And you will also see the metal of the silver is formed as well. In this case, you will see that copper loses electron to silver, so copper is undergo oxidized, right? And then silver would be reduced in this case. Therefore, the oxidation half reaction of this reaction would be copper solid, okay, become copper 2 plus because copper loses electron, okay? And the reduction half reaction would be silver plus become solid silver. And we learned from the previous chapter section, we learned that you need to make sure that the chemical equation of the redox reaction need to be balanced, both the number of element and also the charge as well. And in this case, the number of elements for both half reactions already balanced. The only problem that is not balanced yet is the charge, right? So copper 0 to copper 2 plus, so this is not balanced yet. In order to balance the charge, after you consider the number of element already, the next thing is to look at the charge. So you can go ahead, right? So add 2 electron here, because the 2 plus add to 2 electron that would neutral each other out. Therefore, it will equal to the charge on the right hand, on the left hand side. Do the same thing for the reduction half reaction, because the number of element already balanced. The next thing is to balance the charge by adding electrons. So I'm going to do the same thing here. We need 1 electron on this side, because 1 electron plus positive charge is going to neutral each other out, so that therefore it's going to equal the right side. Okay, and before we can combine these two, right, you will need to make sure that you actually have the number of electrons are equal. Therefore, we are going to multiply the reduction by 2 for the whole thing. Therefore, in this case, you are going to get 2 silver ions, okay, plus 2 electrons become 2 silver solid. And you can see that both elements are equal and also the charge equal as well. And because the number of electrons now are equal, therefore we can cancel the number of electrons, right? So you can combine between these two, right? You can combine the oxidation half reaction and reduction half reaction, and you are going to get the balance equation, which is going to be the one up here. So it would be 2 silver plus copper become copper 2 plus and plus 2 silver solid. Okay, so that would be the balance equation. And the spontaneity of this process would be spontaneous, because once these two submerge in each other, then you observe the color change, and the color change is the identity of the chemical reaction, right? So that means in this case, the reaction happened, the reaction is occur, therefore indicate that the reaction is proceeding forward direction spontaneously. So therefore in this case it would be spontaneous in the forward direction. Next, we are going to learn about the galvanic cell that is based off this reaction right here. So I'm going to use this reaction as a galvanic cell, and I'm going to go over what are the components of galvanic cell. And because I don't have enough space here, so I'm going to erase this part, okay, so that way you see picture better. Here is the picture that display the galvanic cell or voltaic cell. The electrochemical cell is comprised of 2 half reaction, which are the oxidation half reaction and reduction half reaction. And because in the electrochemical cells, the physical contact between the 2 reactants are prevented, therefore we will need to connect those two into the external circuits that connect the half cell together, and we call these electrodes. The electrode at which oxidation occurs is called an anode, and the electrode at which reduction occurs is called cathode. And the way that I memorized cathode and anode is anox, red cat, right? So an mean anode, ox mean oxidation, anode is oxidation, red cat, right? Reduction is cathode. And the last component of the electrochemical cell is called the salt bridge. The salt bridge is a tube filled with the inert electrolyte solution that help maintain charge balance and to complete the circuits as well. And here is the picture that describes the component of the electrochemical cell. So pretty much the physical contact of the 2 reactants are prevented, and you can connect the 2 half reaction by the electrode, right? So this is the electrode, right? Copper is part of the anode because copper happen in the oxidation half reaction. On the other hand, silver would be cathode because silver happen on the reduction half reaction, and these would connect it through the external circuits, right? And the electron would flow And you're also going to see the salt bridge as well that allow the flowing of the ions to balance the charge within the electrochemical cell, or in this case it would be galvanic cell, because we are based off the spontaneous redox reaction between the silver ion and copper solid. Okay, so let me walk you through each of these real quick. So pretty much what happened on the oxidation half reaction is that you will see copper solid, right? So this is copper solid right here. It's going to lose electron, and that electron is going to travel. So that means in this case, the direction of the electron flow is going to go through this Y right here, right? So the electron would flow through that, okay? And it's going to go from the copper anode to silver cathode. Therefore, in this case, you will see that the anode would be the electron rich because it's producing electron. Therefore, we can identify the charge of this equal to negative, right? So the anode would be the negative charge because it produces a lot of electron, and electron would flow from a higher concentration of the electron to a lower concentration of electron. In this case, the silver would be the one that accepting that. Therefore, the flow of electron would go from anode to cathode in this case, right? So that's why we have the arrow there. Okay, so now what happened then? Okay, so on the cathode side, the silver ions that floating in the solution would then accept the electron, right? According to the reduction half reaction, it's going to accept the electron as the electron travel from the anode to cathode. As the electron travel to here, this silver ion will accept the electron, and it's going to become silver solid, right? So silver solid will start to deposit on this side of the reaction. And what you will see is that over time, the concentration of the silver ions will deplete, right? Because the silver ions now become the solid ions. Therefore, silver ions plus will deplete. So you have less concentration of the positive. So that means in this case, the charge will be unbalanced because you're going to end up having a lot of the nitrate ion that is highly negative charge. Therefore, because the charge unbalanced, you need to have something to balance that charge. And this is when the salt bridge come play, right? The salt bridge contain the electrolyte such as sodium nitrate or potassium nitrate or potassium chloride, pretty much any soluble ionic compound, right, that are soluble, those will consider to be used in the salt bridge, right? So most of the time we will use the pH neutral salt it will be considered to for using in this, right? So what happened then in the salt bridge? Because salt bridge contain sodium ions and nitrate ion, and if you consider the beaker that contain the cathode part, right? Because you have the concentration of silver ion to decreased, but the concentration of nitrate stay the same. Therefore, at that point, you are going to have more of the unbalance of the negative charge. Therefore, to make this solution to be neutral, the flow of the sodium ion will flow toward the cathode to balance the charge that is disappear, right? To balance the silver charge that disappear. And on the other hand, if you're looking at the oxidation half reaction, over time, you are producing more copper 2 ions. So therefore, in this case, you end up with more of the cation than the anion is available. Therefore, in this case, the anion, which is part of the salt bridge, would then travel toward the anode to balance the charge for that. So therefore, in this case, the salt bridge will help maintain the charge of the solution by the flow of the cation to the cathode and the flow of the anion to the anode. Another thing that you can memorize is that cathode, right? Cat go together, right? Cathode go with cathode. Cation go with cathode, right? Anion go with the anode, right? So that's how you can use to memorize this. You will see more example of the galvanic cell, which is this diagram here on chapter 18.3, which is the next section. So in this chapter section, pretty much you will just need to understand the conceptual part of the electrochemical cells and what are the components of it, and know the difference between the galvanic cells versus electrolysis cell.